Hello all. In this video, I'm going to prove the generalized Hölder inequality for the product of three functions. Hölder's inequality is one of the most fundamental tools in real analysis. It is equally applicable in measure theory and partial differential equations. Most students first learn it for the product of two functions. Here, um, in this slide, we will see how the inequality extends naturally to three functions. So I'll go step by step, carefully explaining the choice of exponents and each application of order inequality so that the logic is completely clear. So this video is suitable for senior undergraduate students who are studying real analysis and the graduate students who are preparing for the qualifying exams in real analysis and for the research students who are in their research areas like PDs and functional analysis. So let's begin. The statement is if we have x comma mu as a measure space and uh, p, q, r are the numbers which are greater than 1 that satisfy this equality 1 over p plus 1 over q plus 1 over r is equal to 1. And if f belongs to LP, Z belongs to LQ, and H belongs to LR, then we have this inequality. So the norm, L1 norm of the product FGH is always less than or equal to the LP norm of function F times LQ norm of function Z times LR norm of function H. So to prove this one, the idea of the proof is uh, let's consider the Hölder inequality. Generally, it applies for two function. If we have the measure space x mu and p and q are two numbers in between 1 and infinity, that satisfies 1 over p plus 1 over q equals 1. If f is a function in LP space and g is a function in LQ space, then we have this inequality. So this is integration uh, of the product of function fx and gx. We use the absolute value sign and take the non-negative values. Uh, this integration is taken over all the measure space x, and this is less than or equal to this integral to the power 1 over p multiplied by another integral power 1 over q. Or in terms of norm, we can write fg norm of fg, this is L1 norm, is less than or equal to LP norm for f and LQ norm for g. So to handle three function, we need to group two of them together, and then we apply Hölder inequality, and again we apply Hölder inequality. The key step is choosing the correct intermediate exponents in order to prove the Hölder inequality for three functions. So the proof starts from here. It is given that we have 1 over p plus 1 over q plus 1 over r equals 1. Now we define 1 over q plus 1 over r by new variable s. We are taking here reciprocal of s. So 1 over s is equal to 1 over q plus 1 over r. Then the equality now becomes 1 over p plus 1 over s equals 1. So now we can apply the Hölder inequality for function f and gh. So here are two functions, function f and function gh. So we first apply the Hölder inequality for two functions f and gh. So this is the way. So f, gh can be separated in terms of this integration and second integration. The first integration is for the function f to the p, and second integration applies to function gh to the power s. So equivalently, we can write FGS. I mean, L1 norm for FGS can be written as this inequality, LP norm for F, and then LS norm for GH. Now we split the GS term. So this is the GS term. We need to split. So it remains the same and GS term split. Um, so again, we recall here. We consider 1 over Q plus 1 over R is 1 over S. Now we define another variable, another exponent A, which is Q over S, and another exponent B, which is R over S. And then 1 over A plus 1 over B can be written as S over Q plus S over R. This is equal to, this is equal to, we have here 1 over Q plus 1 over R times S. So 1 over Q plus 1 over equals 1 over S. So 1 over S times S. So S divided S will be equal to 1. So we can apply the Hölder inequality for two exponents, A and B, because the condition holds here. So we have the product GH. So now we can apply GH. We can apply Hölder inequality for GH with exponent S here, with exponent A and B. So let's consider two functions, G to the S and H to the S. Now G to the S and H to the S, this is L1 norm. This is less than or equal to, we have the exponents A, B. So this is the function G to the S. This is given function to the A, and this integral, we have this integral. We need to write here the exponent 1 over A. Similarly, for function H to this, we have this integral and to the power 1 over B. So this implies that if we take the power 1 over S, then this integrand, we can use a simply product rule, and the absolute value of GS to the S equals absolute value of G and to the S, S to the power S. So this is less than or equal to GSA here, d mu 1 over A to the power 1 over S. And here we have here integral of HS to the power B whole to the power 1 over B whole to the power 1 over S. Because we know we have this definition here, A equals Q over S. So Q equals A multiplied by S and R equals B multiplied by S. So we have this definition, Q equals SA and R equals SB. So from this one, we can write, oh, this is here. Okay, so this will be equal to GH here. GH norm, I mean LS norm for function GH is less or equal to LQ norm for G multiplied by LR norm for S. And consequently, after this, we have combining both Hölder estimates 1 and 2, we can write FGS L1 is less or equal to FLP ZLQ and HLR. That means we can omit this L and then write FGH 1 sub 1, norm of F sub P, norm of G sub Q, norm of H sub R. So this there is a inequality sign. So this is called the generalized Hölder inequality. This argument extends to the product of more than three functions, and the basic idea here is we split the exponent sum into two Hölder compatible pieces, and it is a fundamental tool in PD's harmonic analysis and probability too. Thank you.